A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be discussing about the Lagrangian and Eulerian description of quantities. So let us get started. The topics for today's discussion will be as follows. We will start with a recap of material and spatial coordinates, because it is important to understand material and spatial coordinates to be able to understand Lagrangian and Eulerian description of motion. Then we'll talk about inverse mapping, that is, to go from spatial coordinates back to the material coordinates. We will then introduce Lagrangian and Eulerian description of quantities, and then we'll solve a couple of problems to reinforce our understanding of material, spatial, Lagrangian, and Eulerian descriptions. So let us get started. So we had introduced the ideas of material and spatial coordinates in the last lecture. So we agreed on the fact that we'll be choosing the same coordinate systems to denote the material coordinates as well as the spatial coordinates for convenience in this course. Although depending on the situation, we can choose different coordinates for representing the material coordinates and the spatial coordinates, that is the reference configuration and the future configurations. So to reinforce our understanding of these ideas, I'll give you a situation. So let's say we have a reference configuration. This we'll call reference, which in most situations is usually the initial configuration. So we say the reference is defined as the configuration that the body takes at t equals 0 in this case. So that is also the initial configuration. And we have a point A, and then later the body moves to a new configuration, that's the current configuration or the deformed configuration. So let's call it the configuration at t equals t1, that is some later time. And the point A has now moved to A prime with the displacement of A denoted as this vector. We will denote this displacement with a u vector and put a superscript A because we're talking about the displacement of the point A as the body moves from one configuration, that is the reference configuration, to the other configuration, that is the current configuration. Again, we can also call these as the undeformed and the deformed configurations. For understanding, let us give these points some coordinates. So let's say the point A is at coordinates 1, 2, and then A prime, which moves to the right, let's say it is 1.5, 0.5. So these are the coordinates of the points A and A prime, which is basically, points A and A prime denote the same physical material point A. So that is, the point A moves from 1, 2 to 1.5, 0.5 from the reference to the current configuration. So with the availability of the mapping function chi, if I substitute the value 1, 2, which is the material coordinates, that is at t equal to 0. So this refers to the material coordinates. Remember, material coordinates are the coordinates of the point at some reference configuration. So this 1, 2 point in space is the point occupied by point A. And since the reference configuration never changes, 1, 2 in the material coordinates is basically referring to the point A at all times. So in this chi function, I put in 1, 2 as the material coordinate of point A, and I specify T1 for the configuration I'm interested in, and this gives me as a result the point A prime, that is 1.5, 0.5. So that is the beauty of the function chi, which if you feed in the material coordinates corresponding to a given point and some later time t, in this case t1, it gives us the coordinates of the particle at a later time in the spatial coordinate system. Now let's consider another point that we'll call the point B, which was here at time t equals 0. And this point B, interestingly, has moved to this point, which is having the coordinates of 1, 2. So this I'll call B prime. So in the material coordinates for capital XA, we have the coordinates 1, 2, which corresponds to the spatial coordinates at t equals t1 as small x of A as 1.5, 0.5. And this point B that we have just shown, let us say its x coordinate was 0.7 and its y coordinate was 2.3, which has now moved to the spatial point, which is given as 1, 2. So this spatial point 1, 2, if you look at that point over time, what you will see is that at t equals to 0, the particle A was sitting there, and at a later time, t equals t1, particle B is sitting on that point. So spatial points or spatial description is that one where we fix our interest on a given spatial point, in this case, for example, 1, 2, and we try to find or look for all the particles which cross that point in space. So I'm sure the idea of material and spatial coordinates is clear now. Material coordinates are fixed, they do not change with time, and they basically are proxies for particles in a given body. If I give you the material coordinate, then that basically corresponds to some particle in the body which was sitting at that point at t equals to 0. That is our choice of initial or the reference configuration. And for spatial descriptions, as we change time for a given fixed spatial point, different particles will cross that point. Now, mathematically speaking, we said that our function chi, or sometimes we write that as simply x, mathematically has to be single valued. So what that means is that for a given input to the function, which is capital X and t, it maps to a unique spatial point. So if my particle P has material coordinates capital X and I specify some later time, then the particle P will be sitting at a unique position at later time. The particle P cannot be at two different places at a later time. This is the meaning of single valued. This function is invertible. So what that means is that if I specify a spatial position at some time t, then that uniquely corresponds to the particle P in the material coordinates. That basically means that at a given position in space, at a given time t, the particle sitting there maps uniquely to its material configuration. So two particles cannot be sitting at the same position at a given time. Mathematically, this function chi has to be continuous. Now, what is the meaning of that? So chi is a function of capital X and t. Let's talk about continuity in space. That is a bit more complicated to comprehend. So let us say for a given point P, this corresponds to some spatial point small xp at a later time. And if I slightly change my input to the function, let's say I pass in xq to chi, which corresponds to small xq. Now this P and Q were points close to each other in the reference configuration, then what this continuity idea means is that P prime and Q prime will also be close at later times as well. So this is the meaning of continuity of the function chi. So in words, I can say that two points which are close in the reference configuration will also be close in the spatial configuration at later times. And the fourth mathematical idea associated with the function chi is that this function is smooth. So this means that the derivatives in space and time are all continuous. And we'll talk about derivatives up to the orders that we are interested in. So there is a chi inverse possible which takes in some spatial coordinates and time, and this tells us the material coordinates of the point which is sitting at these coordinates at this time. So given a particle's position at time t, you will get its original position in the reference configuration. So this chi-inverse function sort of lets us trace back the particle in time to its original or the reference configuration. Mathematically speaking, the inverse function will exist if the Jacobian determinant for this transformation is non-zero. So the Jacobian matrix is defined as del small xi upon del capital Xa. You can see we have two free indices. So this is like a second order tensor, or I'll choose the word matrix here. And when we take the determinant of that, this becomes the Jacobian determinant, or sometimes we use the word Jacobian simply for this quantity, which is actually the determinant of the matrix in this case. So this quantity being not equal to 0 is the condition for the inverse mapping to exist. So this is the expression for the Jacobian determinant. So given the chi function, that is x as a function of capital X comma t, you can differentiate the different components of the vector small x with respect to capital X1, capital X2 and capital X3 and evaluate, this is the determinant here, this determinant, and check if it is not equal to 0, only then the inverse mapping is defined. We will talk more about this matrix in the next few weeks because this is an important matrix for our discussion on deformations. We will also see later that the Jacobian determinant is actually the ratio of the volume in the current configuration. I use a d omega because we talk about infinitesimal volumes in general, to the volume in the reference configuration. So from the physical argument, we can see that this quantity j for any given transformation chi, or the function chi, cannot be negative because that would mean that the volume becomes negative, which is physically impossible. And this being 0 means that the volume has collapsed to a point which again physically is impossible. So Jacobian physically will always be a positive quantity. But this is something we will derive later in the next week. To reinforce whatever ideas we have discussed till now, let us solve a couple of problems now. So the motion of a body is given as this, which basically is our chi function. So first we have to determine the path of a particle P, which was originally sitting at the material coordinates 1, 2, 1. So that is what the chi function allows. It allows us to find the spatial coordinates of some particle, that is P in this case, given the material coordinates of the point, that is its position in the reference configuration, and the time at which we want to find its position. The time is important here because if I change my time, then the particle will move to some other place. So in this case, instead of finding the position at some unique time, we have to find the path of the particle. That is, we have to trace all the positions in space where the particle crosses through over time. And as a part B, we must determine the velocity and the acceleration of the same particle p at a specific time, that is t equals 2. Now note that with this mapping chi that is available to us, we can find the complete velocity field and acceleration fields. That is, we can find the velocity and acceleration of all the particles as a function of their material coordinates capital X and time t. But in this problem, it is asked that we have to focus on some particular point, find its path, and find its velocity and acceleration at a specific time, that is t equals 2. So let us solve the problem. So let us solve part A first. In fact, what we'll do is, since we are given the material coordinates of point P, we will substitute that in the chi function to make it simpler. So small x1, which is the first component of particle P over time, can be written as 1 plus 2t squared, and small x2 is t squared plus 2, and small x3 is simply 1. Now our life is much easier with this because we have to find the path of the particle p, or the trajectory of the particle p. That is, in space we have to find the path that the particle p takes. So trajectory is a curve which does not have time in it. So we'll have to eliminate time because what we are given right now is a parametric form. So let's get rid of the parameter t here, and that's easy to do because we have t squared in both equations. So we can easily eliminate t squared by substituting t squared from the first equation into t squared in the second equation. And when we do that, we get x1 minus 2x2 equals minus 3, and x3 simply is 1, which does not change. So this is obtained by eliminating t. So from the first equation, we see that this is an equation of a straight line. So the particle moves in a straight line. And the second one says it moves in a straight line in the plane x3 equals to 1. So it moves in the x1, x2 plane with x3 equals 1. Now we solve part B. So in part B, we have to find the velocity of the particle p at some time, that is t equals to 2. And we define velocity as d by dt of its spatial coordinate small x, which is written as a function of capital X and t. And this we could easily write as partial by partial t of small x function, for the reason that the material coordinates do not change with time. They are independent of time. So let's do it for v1. So v1 is partial by partial t of x1, and x1 was given as capital X1 plus t squared times capital X2. So which simplifies to 2t capital X2. Now remember, this is for the particle B. So V1 for P is 2. Now the time given is 2 units, and X2, which is the X2 coordinate of P, which was also given as 2. So this becomes 8. And I'll let you do it yourself, and you will find the velocity vector for point P will be the vector 8, 4, 0. And similarly, the acceleration for point P, which is partial by partial t of the velocity written as a function of capital X and t, and this will come out to be 4, 2, 0. So this completes the problem. Now in the problem that was given to us, which was basically this chi function, we can see that in the matrix form, we can express this as the vector small x, and then you have a matrix times the vector capital X, and the matrix in this case is 1 t squared 0 t squared, sorry, this was t squared x1, 1 and 0, and 0 0 1. So mathematically, can you see a linear transformation here? This was the material coordinates or the position of the particle at t equal to 0, and this is the vector which denotes the position of the particle at some later time. And this is a matrix which is a function of time, because as time changes, the spatial position of the particle will also change. So we can represent motion, that is, we can represent the chi function as a linear transformation, or we can say that there is a matrix associated with the motion. So this motion, which we represent using the chi function, is also sometimes called a transformation. So if I specify this matrix t to you, which is a function of time, then I have specified the motion that is taking place. So you'll see in problems or in discussion, we will sometimes be referring to this as motion or sometimes as a transformation. They both mean the same thing. Now, if the transformation contains information about how the particle or the particles in the body move over time, the transformation will be a function of time. And if we are talking about only two configurations, that is, one is undeformed and the other is deformed, then our transformation matrix will not be a function of time. So let us solve another problem. So let us look at part A in the problem. We are asked to invert the transformation that was given in the previous problem. That is, we have to find chi inverse. So in the previous problem, we were given capital X, small x1, small x2, and small x3 in terms of capital X1, capital X2, and capital X3. Let me quickly go back and show you the matrix. So if I want chi inverse, that basically means I want to write capital X vector in terms of some matrix times small x1, small x2, small x3. So given the spatial coordinates and some time, we want to trace back as to which particle or where was the particle sitting at in the reference configuration. And part B asks us to find the velocity and acceleration of the particle that is at this spatial position. So it basically is asking us to find the velocity and acceleration of the particle which is sitting at this point 101 at t equals 2. So let us solve this problem. So inverting the transformation is simple in this case. We don't even have to write the matrix, because first we were given, so this was the original transformation, that is chi, and if I chi inverse, we have to write capital X's as a function of small x's. So first we'll write capital X3 equals small x3, because that is straightforward. And then to find capital X1 and capital X2 in terms of small x1 and small x2, we have two equations and two unknowns. So I'll use these equations to write capital X1 and capital X2 in terms of small x1 and small x2. So when you do that, you will get this. So you can see that I've written the capital X vector in terms of the small x values. Now in part B, we are asked to find the velocity of some particle p and the acceleration of some particle p, which was at a specified location, that is 101, which is the small x vector for p at t equals 2. Now in the previous exercise, we had found out the velocity field as a function of capital X and t, which was found out to be 2tx2, comma 2tx1, comma 0. All we now need to do is to substitute for these capital X1, capital X2, and capital X3 using the chi-inverse transformation we just found. So when you do that, and I will let you do it, you will get these three velocity components as a function of time and their spatial coordinates. So with this functional form, if you have the position in space and some time value, you can find out the velocity of the particle that is sitting at that position at that time. And since we want to find the velocity of a given particle position and a given time, you can substitute these and get the value that is required. I'll let you do it, and I'll also let you figure out the acceleration field as a function of small x and t, and then use that to find the acceleration of the point P, that is the acceleration at small xp at the time t equals 2. With this, I think we are now ready to talk about Lagrangian and Eulerian description of quantities. So let's get into that. Actually, without even knowing, we have been doing that. So we have already figured out what this is. We simply have to give it a terminology. So let us say we're talking about the physical property density. So we'll be using that for our discussion right now. And this density, let's say you have the reference configuration of a body where you had a particle, let's say particle A, sitting here, and to find the density at this point where particle A is sitting, I will need a function of a kind where I specify the ID of the particle, let's say in this case particle A, and the time which is t equal to 0 in this case, and this will give me the density of the point A at t equal to 0. But we said that we work with the material coordinates rather than working with the IDs. So it's better to work with density as a function of capital X, A, and t equal to 0. So this is the density of, again, the point A at t equal to 0. Remember, this capital XA and writing the ID of A are exactly the same thing. But you may have noticed that I'm writing a t here as well. And the reason for that is that if I specify density as a function of capital X and time, what does that mean? Let's talk about the particle A only. So this is the position of A in reference configuration, which is basically a proxy for identifying the particle A. And this is some general time. So this is the density of the point A at any time t. So this is very interesting because using capital X to identify a particle uniquely in the body, and now we are passing the variable time as well, we are able to track the density of this particle A over time. So till now we only talked about the positions of particle. Now we'll talk about associated properties of the particles. So if you are interested in knowing the information about the particle A is of interest to you, so then you are tracking its properties, in this case the density, as a function of time. And this description of quantities is called the Lagrangian description of the quantity. So in general, density rho as a function of capital X in T is the Lagrangian description of density. So what happens is the point A, it follows a trajectory because the body goes through motion. So all the particles in the body also go through motion. So the particle A moves along a path or a trajectory. And if I want to find the density of the particle A as a function of time, basically at later times as the particle moves, I would want to follow the density of the particle. So in this case, I don't care where the particle is going. All I care about is how its density or any quantity that we are interested in is changing. But there are situations where we are interested in particular spatial coordinates. Let us say this is a point P in space. And I would want to find out the density at this spatial point P with time. Now you see I'm using a small x here because small x denotes spatial coordinates. So this is spatial coordinate of some point P. So you can think of your room and you decide on a spatial point in the room and that you call P. It's like you're putting a probe at the point P in the room, and that probe measures the quantity, in this case the density, with time. Now different particles may pass through that point over time, but we don't care about that. All we care about is how the density is changing at that point P in space. So this description of density, where you write density as a function of small x and t, is called the Eulerian description of the quantity. And given one, we can find the other. That is, if you know the density as a function of capital X and t, and you are interested to find the density as a function of small x and t. Now remember, these are different functions, by the way. So it's better that we use a tilde, let's say, to denote this function, because mathematically when you find the function, they are different. But for general discussion, we tend to write rho as a function of small x and t, and that will come out to be a different function. So given rho as a function of capital X and t, that is given the Lagrangian description, you are interested to find the Eulerian description. And that is possible with the inverse mapping chi-inverse. So in this function rho, which is a function of capital X and t, I simply substitute capital X as chi-inverse of small x and t. And when you simplify that, that comes out to be some other function, rho tilde, as a function of small x and t. Now you may think that why are we doing this? What is the point of describing physical or geometrical quantities as Lagrangian descriptions or Eulerian descriptions? Let's give you an example to understand the reason. So let's say we have a building, a 10-story building, and on the top, that is on the roof, you have a point A. Now let us say that unfortunately some deformation happens and the building now starts looking like this. So the point A goes to this position A prime. So you see that we are interested in what's happening at the point A. It's like you had a probe sitting at that point and you are measuring some quantities over time. So in this case, the Lagrangian description is more suitable. Now let's take another example. Let's say there's a river that flows and you have some buildings on the bank, and you have some vehicles sitting and so on. So in this river, what you'll do is you will have a point P, which we'll call as the spatial coordinate P, and we'll want to know what's happening at this point P. Now, over time, what will happen is that different fluid particles will pass through this point P. But what we care about is what is happening at this spatial position. Is the velocity increasing with time at this spatial position or not? Because if it does, then we must be careful. So in this case, I'll be interested in the velocity as a function of small x and t, in this case, particularly for small xp, if I'm interested in that point P. So this is where the Eulerian description is more suitable. Again, these are typical examples. It does not mean that we do not use the Eulerian description in solid mechanics, or we do not use the Lagrangian description in fluid mechanics. It is just that these are typical examples which will give us an understanding of the motivation behind having different descriptions of quantities or motion. So let us solve a problem or two to understand the idea of Lagrangian and Eulerian descriptions properly. So here's the problem. The motion is given in Lagrangian description, that is, small x1, small x2 and small x3 are given in terms of capital X1, capital X2 and capital X3 and the time. So you see that this is the same kind of chi function that we had earlier talked about. But given that chi function was a function of capital X and t, which was the one that gave you the small x or the spatial coordinates, that is also Lagrangian description. So by the definition of the idea of Lagrangian description, we call this as a Lagrangian description of motion. There is nothing new in this problem except that we are wording the transformation differently. We are saying that the Lagrangian description of motion is given. So that means that you have the function chi given as a function of capital X and t, which basically gives you the small x. So now we have to find the Eulerian description. That is, we want to find out the chi inverse, which takes in the spatial coordinates small x and t, because in Eulerian description, you fix your interest at specific position in space and find out what happens to the quantity over time. So this is the function we need, which is actually equal to capital X. So I'll not do it. I will let you do it yourself, because we did it just now in a previous problem to find chi inverse given the transformation or the Lagrangian description chi. And when you do that, this is the answer you should get. So please do it yourself and check the answer. This exercise asks us to find the velocity and acceleration fields for the above motion. And it mentions that we should specify both the Lagrangian and Eulerian descriptions of the velocity and acceleration fields. So what that basically means is that we have to find the velocity as a function of capital X and t, and also velocity as a function of small x and t. So what this, that is a Lagrangian description, gives us is that you feed in the ID, or basically the material coordinates of a particle, which tells us uniquely about some physical particle, and the time, and it tells you the velocity of the particle at a later time. Whereas in the second description, that is the Eulerian description, what it says is you specify some spatial point coordinates and the time, and it tells you the velocity at that spatial point. So in the Lagrangian description, we will be interested in following the velocity of a given particle p. In the Eulerian description, we'll be interested in finding the velocity at a given spatial coordinate. And similarly, you have to find the acceleration a in the material coordinates and acceleration in the spatial coordinates. Now, how did we define velocity? Velocity was d by dt of the small x vector, which is written as a function of capital X in t. And this we said we can easily write as partial by partial t of the small x vector as a function of capital X in t, for the reason that capital X's are independent of time because they are material coordinates or the coordinates of particles in the reference configuration, and the reference configuration does not change with time. And once you find this, you can find the Eulerian description by simply using the inverse mapping chi-inverse. So once you get the velocity as a function of capital X in t, you can find the velocity as a function of small x in t by using the inverse mapping chi-inverse. So in the next lecture, we'll talk about the idea of material derivative, which will clarify this idea or the confusion that people have while finding velocity, acceleration, or basically the time derivative of any physical or geometrical quantity. So thank you very much, and I will see you in the next lecture.